Conservation bar charts are very simple diagrams that you can use to help you understand what's going on in the system. And today we'll be looking at conservation bar charts for momentum and for energy. And so let's start off with momentum. So it's important to remember that momentum is equal to the mass of an object times its velocity. And so if we want to write a conservation bar chart for a piece of clay that's moving through the air, it's falling and it's about to hit the ground, then we'd say that it has a non-zero momentum. And then we'll define the final stage as the moment right after it hits the ground. And so we can split this into three parts. So for our conservation bar chart, we'll have to have the initial part, and then the second part would be delta, which is change in, otherwise known as the impulse, which is the change in momentum, and then final. And then the last thing that you'll need is a horizontal line going through like that, which will essentially be our zero line, and anything above this line will be considered positive, while anything below this line would be considered negative. And so we defined our initial stage as the piece of clay dropping down towards the earth. And we also mentioned that this piece of clay has a non-zero negative momentum because its mass is positive, since mass is always a scalar quantity, and velocity is a vector quantity. So the velocity is also going to be non-zero, but since it's a vector and it's moving down, then we could define that as negative. And so a positive times a negative would give us a non-zero negative answer. Now for our final stage, we said that it was going to be the moment right after the ball hits the floor. And so now it's stationary and its velocity is going to be zero. And in this case, it doesn't matter what the mass is because anything times zero is going to be zero. So you could just write zero there. And since this is a conservation bar chart, you have to make sure that whatever is on the left side of this line is going to equal the right side. And so that's not true in our case right now because we have a non-zero negative number, and that does not equal zero. So we have to put something here in the impulse or change in section to make it equal to zero. And so I'll just pick an arbitrary number for this. I'll say that this is equal to -3. And so the easiest way to make this left side equal to zero is to make the impulse a value of +3 newtons times seconds. And so the -3 and the +3 cancel each other out, giving us a zero for the momentum, and that equals the final momentum, which is also zero. So we've completed our conservation bar chart for this example, and now let's move on to a conservation bar chart for energy. So instead of having P as our momentum like we had in the other bar chart, we're going to use potential and kinetic energy. So potential energy is a capital U and kinetic energy is a capital K. So again, we'll split our bar chart into three parts: initial, change in, and final. And we'll have our horizontal line, which is zero. And then on the initial and final sides, we'll have to have our potential energy and kinetic energy. And you can put little subscripts for initial and final if you want to. Now, let's say that we have a piece of clay again, and you're holding it above the air. So it's a few meters above the ground, and that will be our initial stage. And then we'll define the final stage to be the moment after it hits the ground. So it's almost like the one that we had before, except in this case, we'll be defining the initial stage as holding the piece of clay up in the air and it's not moving. And this is where defining your system will be very important. So let's say our system consists of the earth and the clay. And so in the initial stage, we'd say that the piece of clay has gravitational potential energy because we're holding it up in the air and it has the potential to be pulled down. The only thing that's stopping it from hitting the ground is that you're holding it in the air. And so if you want to specify this to be gravitational potential energy, you could put a little g subscript, and that energy would be positive. And then the kinetic initial energy would be zero because it's moving at 0 meters per second. You're just holding it and it's in the air stationary. Now for the final stage, it also has no kinetic energy because it hit the ground and it's now stationary on the ground and it's not moving. So we'd also have to fill in what we have for the potential energy. So this would also be 0 because it's not being held up above the Earth anymore, and once it's hit the ground, it can't really move anywhere else. It doesn't have the potential to move even further down. And so, like we said before, we'll have to do something so that the left side equals the right side. And I see that the only way we can really do that is to have a negative bar going down here, which will cancel out the effects of this bar. And so we can just erase this for now and say that we have a bar of equal magnitude the opposite direction as the bar we have here. And so these two will then cancel out to make 0, and we'll have 0 on this side and 0 on that side. So that's basically it for conservation bar charts. Just remember that whatever you have on the left, which is initial and change in, equals whatever you have at the final stage.